All right, so now we have a discontinuous integrand. So we have some vertical asymptote here, or here, or here, that's breaking up our graph, and we're going off to infinity with that function that's inside of our integral. So we have three situations. We have, it's going to be at the end, so our x is at x equals b, or it's at the beginning, so it's x equals a, or it's somewhere in the middle, so there's an x equals c that we're looking at. And we have three different ways of writing it. So what we do first is, if it's an end, then what we're going to do is go, okay, well, the ending letter, the b, is not going to be part of this function that we need. So we're going to say it's the limit as t approaches b from the left, because we're coming in from the left if it's at the end, and then replace it with a t. Now, if it's at the beginning, then we're going to say, well, the a is the one with the issue, so we're going to replace it with a t. And as t approaches a from the positive side, because we're coming in from the right, so from where we would add to it, coming in from the right, and so we say a plus. So coming in from the right, we got to do a plus. Coming in from the left, we have to do b minus. Now, what if it's in the middle? Well, then you just split it right at that point of discontinuity. So we're going to say a to c and c to b. And now this one is one that is on the end. So we would use this formula. And then this one is the one that's on the beginning. So we would use this formula where you replace it. So that c here will have a limit as t approaches c plus, and this c would have a limit as t approaches c minus, because we're coming in from the left and the right. All right, so let's try one. So I've got both here. I've got that point of discontinuity in the middle. So let's find one that's convergent, and then we'll do one that is divergent. So this one has a natural log in it. So it's not really easy to see. If you were to graph this, it would actually come to 0. Like this, and so you see it's at 0, so we can just use 0. But you have to notice the points of discontinuity. So natural log can't have 0 inside of it. So we're getting that vertical asymptote here for the natural log of r. So we have to say the limit as t approaches 0 from the right, t to 1, r ln of r dr. And if you forget, you can always look at the sheet. So this is a beginning, so we're using this one. But you can also see that we are approaching, say, from the positive to it. So this is the one that we use. Now, this is an integration by parts, so let's write it off to the side. R ln of r dr. And so if we make our u equal to ln of r, and our dv is equal to r dr, and we get du equals 1 over r, and v equals, ooh, that looks horrible, v equals r squared with a 1/2, and then that would be dr. And so we end up with uv, so 1/2 r squared ln of r minus the integral of duv, so 1 over r and 1/2 r squared. So that would end up with 1/2 r dr. Just continue. So 1/2 r squared ln of r minus, let's zoom in a little bit, 1/2 times 1/2 r squared. And so we end up with 1/2 r squared ln of r minus 1/4 r squared. All right, so now we just have to finish it. So the limit as t approaches 0 plus, and now we can plug that in. From 1 to t. Now we zoom in, and we work on this problem. So we plug it in. So we end up with the 1 goes first. So 1/2 times 1 squared ln of 1 minus 1/4 1 squared minus, and now the t's. So 1/2 t squared ln of t minus 1/4 t squared. All right. So obviously these are done. This is just some value. So we have 1/2 ln of 1 minus 1/4. So we're going to write that 1/2 ln of 1, which is 0. So we end up with negative 1/4. Okay, now we move on to the next part. Well, if we were to do c of 0 for this one, plugging in 0 from the right, it doesn't matter, it's still a parabola. So coming in from the right of 0, it's still going to be 0. So this one will go off to 0. So we're done with that one. So really, we just have this one right in the middle to deal with. So let's take care of that one. Minus the limit as t approaches 0 plus. And if you look at it, we end up with 0 times infinity. That's L'Hopital's rule. So let's take care of it now with L'Hopital. So this is the limit as t approaches 0 plus. And if you remember, you don't want to put natural log at the bottom. So it would be this instead. And so I'm going to change it to a t to the negative 2. There we go. So we get our negative infinity over infinity. So we can use L'Hopital's. This is the limit as t approaches 0 plus. We're using L'Hopital's rule. And we end up with 1 over t, and then that would be negative 2 over t cubed, right, t to the negative. And so this is the limit as t approaches 0 plus of 1 over t times, and then it'd be t cubed over negative 2. But no matter what, that's going to cancel, giving us t squared. We plug in 0, and we end up with 0. So the limit of that one is 0. So we have negative 1/4. It's nice when it writes the fraction. Negative 1/4 minus 0, negative 1/4. So that is our limit. And so there was our graph. We're going from 0 to 1, and you can see it's negative 0.25. All right, let's look at one that is divergent. So there's the graph. So you can see from 0 to 4, we have a vertical asymptote here right at 2. And where you can find that is if you were to factor this, and we're going to have to anyways, we end up with that. And so we have a point of discontinuity at 2 and negative 1. So x cannot be 2 and x cannot be negative 1. However, negative 1 is not within our interval. So if we are going from 0 to 4, then we have an issue here at x equals 2. So we have to split it. So we go integral from 0 to 2. I'm going to put it in the factored form now. Plus 2 to 4. So what we would have to do now is find the integral of this one, and then find the integral of this one, and then add them together. So let's start with the first one. So we have the integral from 0 to 2 dx and where we're having the issue is at the 2. So this would be the limit as t approaches 2, and you can see that we're on the left side here, so we're approaching from the negative. Integral 0 to t just like that. Now let's perform our partial fractions and go from there. So we know that 1 over x minus 2, x plus 1, is going to equal a over x minus 2 plus b over x plus 1. So we end up with a x plus 1, which is ax plus a, and b x minus 2, which is b. Where'd the x go? I didn't draw it. Ax plus a. There we go. And bx minus 2b. And then there is no x value here, so 0. And our constant is 1. So we have a plus b equals 0. And a minus 2 is equal to b is equal to 1. So a is equal to negative b. So if we plug that in, we get negative 3b equals 1. So b equals negative 1/3, which means a equals positive 1/3. All right, so now that means we can take and find our integral for this. We have the integral of 1 over x minus 2, x plus 1 dx will equal, I'm going to take out the 1/3 now because they both share it. So b is negative 1/3, a is positive 1/3. So we will just say integral of 1 over x minus 2 minus, so I'm including the negative now here, 1 dx, and so this is 1/3 ln of x minus 2 minus ln of x plus 1. All right, and so now we just have to plug it in and show that it is divergent. So we have 1/3 of the limit as t approaches 2 from the left of the natural log of x minus 2 minus the natural log of x plus 1 t and 0. So if we plug that in, 1/3 limit as t approaches 2. Now we're not approaching infinity on this one, so don't just start canceling stuff here and saying, oh, this is infinity. You have to plug it in and look at it. So t minus 2 minus ln of t plus 1 minus, and then now the next one. So ln of negative 2. So that would just be 2. So again, if you plug in 0, it'd be 0 minus 2, which is 2. Plug in 0, be 1. So minus ln of 1, and that's 0. All right, so now if we do look at it as it approaches 2 from the left, now we do have a absolute value here. So as we're approaching it from the left, you would think about it plugging in 1.99, right? And then 1.9999, 1.9999. The difference here is still getting closer and closer to 0. So this inside is really approaching 0. So we know this is approaching negative infinity. This one is just a 2, so if we plug that in, we get ln of 3. So we're going to get negative infinity minus ln of 3 minus ln of 2, and then the last one's 0, 1/3. And so what do we get? Negative infinity. This is divergent. Okay, so if we know that the first part is divergent, there's no reason to even calculate the second part. It doesn't even matter if it converged or didn't converge. It's because this one is divergent. The whole thing is divergent. So no matter what, it diverges. So when you're doing these problems, you do have to break them up. If you have a vertical asymptote at the end, you want to use the first formula. Vertical asymptote at the beginning, the second. And if you just think about what's actually coming here, we're approaching from the right, we're approaching from the left. So that would be from the negative, from the positive, from the negative, from the positive, and you add them up together to make this work. Well, what if you were going off to infinity from here? Well, then you'd cut it again, and you go from that point. So you would go to 2c from the right, 2c, sorry, from the left, 2c from the right, and then you would actually have it from b to infinity, like we would do in the other way. You just add another one onto it. Have fun.